So our first speaker is Steph Sallum of the University of California, Irvine. Our talk will be Scales, Instrument Overview, and Expected Science Outcomes. And again, just want to reiterate, while you're listening to Professor Sallum, you can discuss the talk on the Zoom channel or the Slack channel, session 1, Sallum_Steph. And we can also keep questions going that don't get answered directly here in our limited time in that Slack channel. So without further ado, Steph.
Cool. Thanks, Chris, for the introduction. I'm super excited to be here and to get us started off today. So I'm going to talk about Scales, which is the Santa Cruz array of lenslets for exoplanet spectroscopy. This is a diffraction-limited 2 to 5 micron integral field spectrograph that's being built for Keck, expected to deploy in 2025. Andy Skemmer at UCSC is the instrument PI, and I'm the project scientist. But Scales is a collaboration between lots of people whose names you can all see on this slide. In particular, I want to highlight Dino Stelter, who's done a ton of design work, and Zach Briesmeister, who's been working on simulations that I'm going to show in my talk. Oops. So as you might have guessed from the name, Scales is designed specifically for exoplanet discovery and characterization. And the unique thing about Scales is its 2 to 5 micron wavelength range. So virtually all other exoplanet characterization integral field spectrographs have operated shorter than 2 or 2.5 microns. And the advantage for this longer wavelength range is that you can detect planets that are cooler and lower mass than what we've been able to detect with similar instruments so far. So this is what the plot on the left is showing, is spectra for a handful of planetary atmosphere models with different temperatures. And you can see that as you get cooler down to something like 700, 400 Kelvin, down to Jupiter type models, the flux rises steeply after 3 microns. So there's an advantage to using Scales to look for planets, which is that you can find these cooler planets that are much harder to image with other instruments. And as an integral field spectrograph, Scales gets you a boost in contrast compared to broadband imaging. And so this is illustrated in this little animation on the right, where I'm scrolling through a cube of point spread functions at different wavelengths. And you can see that with this wavelength information, it's much easier to tell the difference between something like a speckle, noise caused by residual AO errors, from an injected planet. So that you can see the speckle here moves out of the red circle, while a true signal like a planet that I've injected into this cube stays in the green circle. So this is a summary of Scales modes. It's going to have various modes from 2 to 5 microns with both low resolution and medium resolution, spectral resolution. So you can see that there are some modes that are specifically designed for looking for things like PA and methane features and water ice, also broad SED modes and just K through M band. And the figures down here show Scales in the context of other instruments in terms of contrast and spectral resolution. So you can see that Scales will offer better contrast than NERC2 and coronagraphic modes on James Webb at an angular separation of 250 milliarc seconds. And it also carves out a unique zone in spectral resolution parameter space compared to those instruments and other IFSs like GPI and OSIRIS. If you're curious about hearing more on Scales design and updates there, I encourage you to check out Dino Stelter's poster, which is in Group D. So there are a number of science cases that Scales will be exciting for, and I'm not going to talk about all of these in the next 3.5 minutes, but I am going to give you a list of them here. You'll notice that the first 4 are all planetary related, so exoplanet and protoplanet discovery and characterization, monitoring objects in the solar system, characterizing protoplanetary disks in ice features and also PA features. But there are also modes for Scales that will be exciting for other science that might be more interesting to the broader Keck community. So a couple of examples of those are mapping supernova remnants in things like dust and in CO, and also characterizing AGN. So for example, looking for PA features in the inner 100 parsecs or so of tori around AGN. So for the rest of the talk, I'm just going to show a few simulated observations from scales for some of these science cases. So the first one is exoplanet detection and characterization. So here I'm just showing a simulated data cube from one of Zach Briesmeister's simulation tools of an HR 8799 analog, and then the extracted spectra on the right with a few example images. So you can see that as you scroll through wavelength, you can watch the planet fluxes increase, especially as you move longer than about 3.5 microns. And characterizing these planets in this level of detail will allow us to do things like estimate luminosities, masses, molecular abundances, especially with scale's medium resolution mode. Another exciting application in the exoplanet world is characterizing planets that are detected via astrometry. So for example, with Gaia and WFIRST. So this is what's shown on the right here. You can see a expected planet yield for planets that would be detected by Gaia and WFIRST that we'd be able to see with scales. You can see that we can get down to temperatures of 300, 400 Kelvin and masses of a couple of Jupiter masses. So this will be super exciting for benchmarking planet formation models and atmospheric models. Solar system science is another cool one. So this is another animation for the Io volcanoes. And so you can see a few representative images here and the extracted spectrum for one particular volcano. And so by getting a spectrum instead of broadband fluxes, we'll be able to better constrain volcano temperatures and also volcano sizes on Io. Other cool solar system science examples are weather patterns on something like Titan, for example. And so the last one I'll show is protoplanet detection and characterization. So this is a simulation for a circumplanetary disk around a PDS-70b analog. You can see that we'll be able to characterize things like spectral slopes for protoplanet emission. And another exciting opportunity for protoplanets is looking for excesses in hydrogen lines like bracket gamma or bracket alpha in scales' medium resolution mode. Okay, so those are all the examples I'll share with you today. I will just leave you with a few thoughts. One is to reach out with science ideas other than the ones I've talked about, or questions about what I've talked about, or if you're interested in joining the science team. Another is I'm now recruiting for an open postdoc position at UCI, which should be on the job register, where there will be opportunities to work on scales development. And the last one is if you're interested in making sure that scales will meet the needs of the Keck community, make sure to attend Tom Green's breakout session tomorrow at 1 p.m. So that's all I have for you, and I'll take any questions.
Very good. So thank you, Steph. We're taking questions in the Q&A mode from at the bottom of Zoom. So we have one already. Then Curry has asked, what about the coronography with scales?
Yes, scales will have coronographic imaging. I will leave my answer at that for now, and I can share the details about the coronagraphs that we're thinking about on Slack.
That's a good opportunity to get into the Slack channel. Other questions that people have. And while we're waiting for those, can I ask the motivation for the higher resolution modes, which I think you refer to as the medium resolution mode, is that principally for, I mean, perhaps you could expand on that a little bit as somebody who doesn't do exoplanets?
Yeah, sure. So the medium resolution modes will be really useful for doing things like constraining molecular abundances in atmospheres compared to the lower resolution modes. And other cool science that's not just characterizing exoplanet atmospheres. One that I mentioned super briefly was looking for excesses for accreting planets. You need the more like R of a few thousand to get reasonable contrast compared to the star there.
We have another question in the question channel asking what the field of view of the instrument is.
Yeah, so the field of view for the low resolution mode is 2.2 arcseconds on a side, so it's a square. And then the medium resolution mode is more like 0.3 arcseconds on a side. Yeah.
All right, so with 6 seconds left in the Q&A, we'll wrap this up. And thank you, Steph.
Thank you.